Welcome to the online classes. Today our concept is double circuit line. So here in the last class we are discussed the inductance of three-phase transmission line with a single circuit. So now we are going to discuss about the double circuit line of a three-phase transmission line. What is mean by double circuit line? Double circuit line means each phase is having two circuits. Each phase is having two circuits means two conductors. Totally three phases, 3 into 2, 6 conductors. That's why double circuit transmission line refers to the arrangement in which a total of 6 conductors are provided to make two different transmission circuits. See here, like this. Is that right? This is a double circuit line. This is phase A, phase B, phase C. So in phase A, two conductors are there, two circuits, A and A dash, B, B dash, C, C dash. So in double circuit transmission line, there are two circuits, each consisting of three conductors corresponding to three phases. Both the circuits, here double circuits means two conductors are in each phase. Those two conductors are combinedly called as bundled conductors. That's why here both the circuits in double circuit transmission line are mounted or run through the same transmission line. In double circuit transmission line, bundled conductors are mostly used. Bundled conductors means two or more conductors arrangement is called bundled conductor. Bundled conductor increases the diameter. When diameter increases, what happens means resistance decreases, inductive reactance decreases. That means what happens means power loss decreases. And one more important advantage is with the use of bundled conductor, corona can be reduced. Corona means which is a discharge of electric power in the form of loss that can be reduced with the help of bundled conductors. So here anyway, this is a double circuit line. Double circuit line means each phase having two conductors. That means three phases having two circuits, 3 into 2. Two circuits means two conductors. 3 into 2, 6 conductors. And what are the advantages of double circuit line means? First, power handling capability increases. We can transmit more power. That means line enables the transfer of more power over a long distances or particular distance. One more thing is that due to double circuit transmission line, the reliability of power supply increases. These are the two advantages. That for a double circuit three-phase transmission line, how to calculate the inductance? That inductance can be calculated in terms of GMD. So now we are going to discuss about how to calculate GMD for a three-phase double circuit. See here. This is a double circuit line. These are the three phases A, B, C. In these three phases, each phase having two conductors. In the phase A, the two conductors are A and A dash. In the B phase, two conductors are B and B dash. In the C phase, the two conductors are C and C dash. Now, one more thing we are defined here at the starting, no problem. The distance between conductor A and conductor A dash is B A dash. The distance between conductor B and B dash is D B dash. The distance between conductor C and the C dash is D C dash. Mutual distances are A B D A B dash dash. At the same time D B A dash D dash D C B dash dash. Like that, the distances are defined between these two conductors. Here A dash, B dash, C dash also conductors, but second circuit. That's why we will consider the distance between second conductors as well as first conductor. So that's why first the self GMD of a conductor is as usually 0.7788 R, where R is the radius of a conductor. This is for single circuit line. But for double circuit line, this self GMD is, see here now, first we have to calculate DS1. DS1 means which is the distance between conductor A and A dash. That is, see here, DAA into DAA dash into DA dash A dash into DA dash A whole to the power of 1 by 4. Whole to the power of 1 by 4, why we are taken means here in the multiplication 1 by 4 is there. That's why we are taken in the GMD. That is the reason why I am taken here. So anyway, the GMD, the self GMD calculation, first we have to calculate DS1 like this. After the self GMD of a combination BB dash is like this. DBB into DBB dash, DB dash, B dash, DB dash B, where DAA, DBB is nothing but the distance between the conductors. A means conductor A dash means second conductor in A phase. Like that we have to calculate. In a similar manner, DS3 is equal to DCC dash into DCC, DC dash, C dash, DC dash equal to the power of 1 by 4. Finally, equivalent self GMD of one phase is equal to, this is already we are very well known, 1 by 3 is cube root. So here the simplification we are already observed in the previous class. DS is equal to cube root of DS1 into DS2 into DS, or otherwise DS1 into DS2 into DS3 whole to the power of 1 by 3. And the value of DS is the same for all phases. Is it same for all phases? Phase A, phase B, phase C. As such conductor has the same radius. Is that the phase A conductor having same radius, the DS value is same. The conductor A has same radius with the B, C. B, C are same radius. DS is same for three phases A, B, C. And now the mutual GMD between A and B. Mutual means it is two conductors. So that's why here DAB is again DAB into DAB dash, DA dash B into DA dash B dash whole to the power of 1 by 4. And mutual GMD between B and C like this, and C and A like this. Finally, equivalent mutual GMD is equal to DM into cube root of DAB into DBC into DCA, or otherwise DAB into DBC into DCA whole to the power of 1 by 3. Like this, we can calculate the self GMD and mutual GMD. So based on this, we will do one problem. See here, calculate the inductance per phase per meter for a three-phase double circuit line whose phase conductors have a radius of 5.3 centimeter with the horizontal conductor arrangement as shown in figure. See here. Here conductor A, B, C. These are the positions, their respective positions. And here what happened? This is conductor A dash. Second circuit, double circuit line. That's right. The second circuit, this first circuit. So A dash, B dash, C dash, their positions are 1 dash, 2 dash, 3 dash. And here the distance between AB 8 meter, BC 8 meter, CA dash 8 meter, A dash, B dash 8 meters, B dash, C dash 8 meters. So if we can observe the given problem, first we have to calculate inductance per phase per meter for a three-phase double circuit line. So for this calculation, what happened here means first the data is radius is there 5.3 centimeter. Radius of the conductor is there 5.3 centimeter. After that, these are horizontal. So to calculate inductance, the formula is, see here. First we will write the formula. What is that? Means 10 to the power of minus 7 into 2 log E dm by ds Henry per meter. Here 1 by t is also there, but due to the internal flux already neglected in previous cases, we are eliminated. If we are using 1 by 2, it is not at all a problem. The three-phase single circuit line we can use, no problem. At that time also eliminate, no problem. Here also if we can use, no problem. So that's why the problem is 10 to the power of minus 7 into 2 log E dm by ds, the inductance per phase per meter, where dm means mutual GMD and ds means self GMD. First we will calculate these two things. So self GMD means simply GM molecules, that is 0.7788 into R, R value is 5.3 centimeter, while it is converted into meters. This is 0.0413 meter with the GMR of conductor self GMR. So then equivalent self GMD or GMR, self GMD or another name is GMR. So then equivalent self GMD of one phase is, see here, ds value ds1, ds2, ds3 whole power 1 by 3. This is the formula for self GMD. For that, first we can calculate ds1 after ds2, ds3. The formulas are like this. We are already defined that daa is the distance between aa, the distance between aa dash daa. So aa dash means this is a conductor, this is a dash. Total distance 8 plus 8 plus 8 plus 8. Totally 3 into 8, 24. That's why here it is 24. Like this we can substitute, and finally 0.995 meter. Then ds2, this is the formula and this is the value substitution. And similarly ds3 is 0.995 meters. Then finally ds3 equivalent to GMD. So right, like that we can calculate ds3. ds3 means dcc dash dc dash c dash, and at the same time dcc. Like that we have to calculate here. So here self means that means da dash a dash and daa dbb dcc dp dash p dash dc dash c dash. GMR of conductor which is 0.0413 meter. We will is it right? So that's why you can calculate the equivalent self GMD of one phase, right? So next, equivalent mutual GMD. Equivalent mutual GMD is formula is dm is equal to cube root of dab dbc dca multiplication. Dab is dab into dab dash da dash b da dash b dash all to the power of 1 by 4. We can substitute distances, we can calculate the dm value. So then finally inductance per phase per meter 10 to the power of minus 7 into 2 log e dm by ds Henry per meter. Finally 10 to the power of minus 7 into 2 log e 14.518 by 0.995 Henry per meter. Finally 5.36 into 10 power minus 7 Henry per meter. Like this you have to calculate the inductance of three-phase double circuit line in terms of self GMD and mutual GMD. So this is self GMD. DS means DM means mutual GMD. Like this we can get. Next concept is final concept, final parameter, final transmission line parameter is capacitance. What is meant by capacitance? Simply first, what is a capacitor? Capacitor means if two conductors are arranged by a distance of d meters and the separation of d can be filled with a insulating medium. That means when two conductors are separated by an insulating medium, that arrangement is called capacitor, and the function of a capacitor is the capacitance, the property of capacitor. What is the property? Which can store the electrical charge in the form of electric field. Right now, so here the energy stored per unit voltage is called its capacity. That's its capacity is called capacitance. Capacitance is defined as the capability of an element to store electric charge. That's why capacitance is the ratio of the change in electric charge of a system to the corresponding change in its electric potential. That is C is equal to Q by V. That means in order to calculate capacitance, first we have to calculate electric potential after energy stored, charge stored. First thing is that potential we have to determine. So for that electric potential, in that electric potential, we have to determine electric potential for a single phase conductor between two conductors. See here, these are the two conductors. This is a conductor here. Simply the conductor of radius or meter. This is conductor A. The charge on this conductor A is QA, and we have to determine the work done on the moving point charge. Is it work done on the moving point charge? Whenever this simply this conductor is placed in an electric field, what happens here? Due to the electric field stress on the charge can move from one place to another place. That means here, electric potential at the point due to a charge is the electric potential at a point due to a charge. The charge is QA here, which is the work done in bring a unit point charge from infinity to that point. In the lower classes, we are already discussed the definition of electric potential or voltage. The amount of work is done to move a charge from one place to infinity of that charge. That means if this is in conductor A, charge is there. From this conductor A, in order to move the charge from one place to infinity of that place, electric potential is required. Is it that work done? What is the work is required to move this charge from point this particular reference point A to B is nothing but electric potential. When this point is located at x meter distance from the center of the conductor A. That means the concept of electric potential is extremely important for the determination of capacitance of circuit. That how to determine electric potential? Simply we know that. What is that? First we have to determine consider a long straight cylindrical conductor A of radius r meter. These things are already discussed in our physics electromagnetic fields unit. So here cylindrical conductor of radius conductor A of radius r meter in the previous figure. So this is a cylindrical conductor A of radius r meter. After that, this conductor operates such a potential of VA, charge QA. So the potential is required to move this charge from this point to this point is VA, and the charge on the conductor is QA. And the electric field intensity, first we have to calculate electric field intensity at a distance of x from the center of the conductor A, cylindrical conductor A. That means at point P we have to calculate electric field intensity. Here cylindrical conductor means the charge distribution is line charge. That's why electric field intensity at an infinite distance is E is equal to rho L by 2 pi epsilon naught into x. Their distance is x, not r, x here it is. So that's why here simply rho L means what? Rho L means line charge density, which is defined as line charge per unit length here. So that means what happened here means rho L is equal to, in terms of QL you can express this. QL means rho L into L here. QL means rho L into L here. So then rho L means QL by L here. Is that? So then if you can substitute it at that place, here it is per unit length. That's why here volts per meter is the unit. And finally, if you can substitute rho L is equal to QL into L, E is equal to actual formula is electric field intensity due to line charge. That is rho L by 2 pi epsilon naught into x. Rho L is nothing but QL by L into 2 pi epsilon naught into x. So here electric field intensity, but we want electric field intensity per meter length. So that's why E is equal to QL by 2 pi epsilon naught into x. So this is the electric field intensity at a point of P. That P is located at x meter distance from the center of the conductor A. That's why electric field intensity at point P is E is equal to QA by 2 pi epsilon naught x into x volt per meter, where QA is the charge on the conductor A. From this we have to calculate potential. How to calculate potential? We know that E is equal to minus dV by dx, where dV by dx is the potential gradient. In magnitudes, E is equal to dV by dx. So then dV is equal to E dx. So then by applying integration, integral dV is equal to integral E dx. So then integral dV is nothing but integration differentiation cancel out V. Then E is we have E, that is equal to integral QL by 2 pi epsilon naught x dx. So then finally QL by 2 pi epsilon naught is a constant, integral 1 by x dx. It is what happened, R to infinity, right? R to infinity, infinite place. At the point of infinity, the point will move. That is the work done required to move a point charge from initial point to the infinity of that point. First, the point is located at the center of the conductor, that is r meter distance. After that, its final limit is infinity. Anyway, finally, the potential at point A to move the charge from that initial center of the conductor to the infinity place, that is QL by 2 pi epsilon naught integral r to infinity 1 by x dx. Is it? So this is the expression for V8 and this is the expression for E here. After, if V value is known value, C is equal to Q by V. Capacitance means charge stored per unit voltage. That's why we know the V value. What is that V value? Here it is Q by QL by V means VA, no problem. Q means QA, no problem. Why? Because of we have determined the capacitance with respect to conductor A or any other conductor. So then QA by VA is nothing but QA by QL means here it is a conductor, charge on conductor, that is QA by 2 pi epsilon naught integral 1 by x dx r to infinity. That means what happened? QA both are get cancelled out. So that means finally 2 pi epsilon naught by integral r to infinity 1 by x dx. That means if potential is a known value, we will easily determine the capacitance. That's why first we have to determine potential for any type of system to calculate its capacity. Okay, thank you.